Okay, so let's look at some examples. So in number 1, we have the square root of 3 squared. Okay. Remember that the index, or the n, on the square root, when we don't see it, is really 2. So if we use our first example, our first rule, okay, these two match, so the answer should just be 3. Another way to think about this is the square root of 3 squared is the square root of 3 times 3. And since there's a group of 2 3's, the answer is just 3. And we can apply that concept now to number 2, where we have the square root of the quantity negative 3 squared. That means negative 3 times negative 3. And there's a group of 2 negative 3's, so our answer will be negative 3. I do the grouping so it'll make more sense when we get to the cube root. For example, the cube root of 125. This is the index. In this case, n is equal to 3. So instead of looking for a group of 2, we're going to be looking for groups of 3. And if we take the prime factorization of 125, 5 will go into 12 2 times, and then 5 times 2 is 10. 12 minus 10 is 2, so there's a remainder of 2. Now I look at 25. 5 goes into 25 5 times. We continue since 25 is not prime. 5 goes into 25 5 times. So that is, we could rewrite 125 via its prime factorization, which is 5 cubed. Now, our indexes match, so the answer will simply be the base, which is 5. And this becomes helpful, say like in number 4, we have the square root of 12. Okay. Now the square root of 12 is not a perfect base, but if we have the prime factorization, 2 goes into 12 6 times, and 2 goes into 6 3 times, which means we could rewrite 12 via its prime factorization of 2 squared times 3. Now we have a product, and we can use the rule that says when you have the radical of a product, that is a multiplication, it's the square root of the first and the square root of the second. And that helps us simplify the radical, because the square root of 2 squared is 2, and the square root of 3 cannot be simplified. So let's try 5. The square root of 50. First, we need to find the prime factorization. 5 goes into 50 10 times, and 5 goes into 10 2 times. This means we could rewrite the square root of 50 as the square root of 2 times 5 squared. Following in the same manner as above, this is multiplication, so we can take the square root of the first factor times the square root of the second factor. Now the square root of 2 cannot be simplified. However, the square root of 5 squared is 5. And then, by convention, we like to write this as, remember, multiplication will commute, so we like to write that as 5 times the square root of 2. And what this has allowed us to do is simplify the radical. So square root of 50 has been simplified to 5 times the square root of 2. In number 6, we deal with a cube root of 40. And again, we'd like to simplify. The process is the same. We'll take and find the prime factorization. So 2 goes into 40 2 times. 2 goes into 20 10 times. And 2 goes into 10 5 times. This means, copying the radical, this is the cube root. We could write the cube root of 40 as the cube root of 2 cubed, 2 times 2 times 2 times 5. And then splitting the radical, that's the cube root of 2 cubed times the cube root of 5. Now these match, so this simplifies to just 2 because there's a group of 3 2's. And the 5 doesn't have a grouping, so it stays behind. And we have to write in the cube root. It's very important that we put that in because without it, we're talking about the square root. Number 7. Here we have the cube root of 81. Again, same process. Let's find the prime factorization. We know that 3 goes into 81. Might be easier to look at it this way. We know 81 is 9 times 9, and that 9 is 3 times 3. So that means we could write this as the cube root of 3 to the 4th. So there are a couple ways to think about this. We could rewrite 3 to the 4th as 3 cubed times 3. Okay. Remember, there's a first power here. Because when we're multiplying with like bases, we could add the exponents and come up with 4. This will then allow us to split the radical. So the cube of the first and the cube of the second. And now this will simplify to just 3. And then this cube root of 3 has to stay behind because there's only 1. Another way to think about this is just from here. Once I take the prime factorization, I know I'm looking for a group of 3's. There is one group of 3, so I can pull that 3 out. Remember, I need to put in the radical, the index, so it's a cube root. And then I just have to take what's left behind and put it back underneath. So that's 2 different ways for you to think about that. Let's try 8, the cube root of 500. Prime factorization. 5 goes into 500 100 times. 5 goes into 100 20 times. 5 goes into 20 4 times. 2 goes into 4 2 times. Which means we could write the cube root of 500 as the cube root of 5 cubed times 2 squared. And then we can split the radical. We'll have the cube root of 5 cubed times the cube root of 2 squared. Now this will simplify because we see the group of 3's to just 5. And here we only have 2 2's, but what's necessary is a group of 3. So we can't do anything with those. So this just becomes the cube root of, and then we multiply it back out. 2 squared is 4. Number 9. Now in number 9, we're looking at a 4th root. So what we will need is a group of 4's. Well, 4 to a grouping. So, first, prime factorization. 2 goes in to 48 because it's even. 2 goes into 4 2 times, and 2 goes into 8 4 times. 2 goes into 24 12 times, and 2 goes into 12 6 times, and 2 goes into 6 3 times. Which means we could write this as the 4th root of 2 to the 4th times 3. This will allow us to split the radical. 2 to the 4th times the 4th root of 3. Again, these two match, so this will simplify to 2. And we can see that because there's 4 2's in the prime factorization of 48. And then the 4th root of 3 cannot be simplified. There's only a single 3. Number 10. We could look at the square root of 3 25ths. Now we will use our rule number 3 that says that if you have the square root of a fraction, that's the same thing as the square root of the numerator, of the square root of the denominator. Now the square root of 3 cannot be simplified, but we know that the square root of 25 is 5. So in this way, we've simplified the radical. In 11, we have the square root of 6x times the square root of 5y. And first we'd like to look, is there any way to simplify this? Well, 6 is 2 times 3. So there's no grouping of 2's. 5 is simply 1 and 5. So on their own, neither of these can be simplified. However, we could use our rule about multiplication and radicals. So we know that this becomes the square root of here 6x and here times 5y. Which is equal to 6 and 5 are 30, and x times y are xy. And if we could, we would simplify this radical. We'd be looking for groups of 2, because we're in the square root. But the prime factorization of 30 is 3, and then 2, and then 5, which we can see from here, 2 times 3 times 5. So there are no groupings for us to pull out of here. There's only a single x and a single y, and so this is our simplified answer. Let's do another. In number 12, we have the square root of 6x, but now let's say I multiply that by 2x, square root of 2x. Well, again, they're simplified on their own. However, when I combine them, I'll take the 6x and multiply that by the 2x. Which now simplifying under the radical is 12x squared. And this I know can be simplified. We can split this up into the square root of 12 times the square root of x squared. We've done this before, but let's do it again. To simplify radical 12, we take the prime factorization. And from here, we can see there's a group of 2's. So radical 12, root 12, is the same thing as 2, but there's a root of 3 left. Now the square root of x squared, the same thing will happen. The squared and the square root will undo each other, so we're left with x. Then we'll like to commute things around and put that x next to the 2, so we get the square root, 2x times the square root of 3. Let's keep going with number 13.